Your query against the orders table just spiked to 12 seconds. You have indexes on customer identifier and order date, but the query uses both in the where clause. The database engine is performing an index merge or a full table scan because two separate B-tree structures cannot efficiently intersect large result sets. The fix is a single multi-column index. We are not simply concatenating columns, we are creating a hierarchical search structure. This composite index must be defined with careful column ordering to ensure maximum utility across your most critical query patterns. Misordering the columns renders the index useless for most common lookups, forcing the optimizer back to inefficient plans. We will immediately define the critical rule governing this structure, the leftmost prefix rule. A composite index on columns A, B, and C is internally structured as a sorted list, where A is the primary sort key, B is the secondary sort key within A, and C is the tertiary key within B. This structure dictates query eligibility. The leftmost prefix rule states that the index can only be used if the query references the leftmost column, A, or any contiguous prefix starting from A, such as A and B or A, B, and C. If your query only filters on B and C, the index is unusable because the B-tree structure is sorted primarily by A. For example, an index on state, city, street is effective for queries filtering by state or state and city, but not for queries filtering only by city. Understanding this hierarchy is the foundation of effective composite indexing.
When designing the column order, place equality conditions before range conditions. An equality condition, like user identifier equals 42, allows the index scan to jump directly to the relevant block. A range condition, such as order date greater than 2023-01-01, stops the index from utilizing subsequent columns for filtering. Consider an index on status, created at, amount. If the query is where status equals pending and created at greater than 2023-10-01 and amount greater than 100, the index uses status for direct lookup, then uses created at for the range scan. Crucially, the index cannot use amount because the range condition on created at breaks the contiguous prefix search capability for the remaining columns. Therefore, place the most restrictive equality columns first to maximize index utilization depth. Index selectivity, the ratio of distinct values to total rows, determines the efficiency of the initial index lookup. High-cardinality columns, like email address or universal unique identifier, are highly selective and should generally be placed first if they are frequently used in equality lookups. Low-cardinality columns, such as isActive or gender, result in large index scans and should be placed later, typically after high-cardinality equality columns. If a query frequently filters by tenant identifier and user identifier, and tenant identifier has only 5 distinct values across millions of rows, while user identifier is unique, placing tenant identifier first is inefficient. The optimizer must scan 5 massive blocks. Reversing the order to user identifier tenant identifier is usually better, unless the query always includes an equality filter on tenant identifier, which is necessary for partitioning.
Composite indexes are not only for filtering, they can eliminate expensive file sort operations. If your query includes an order by clause, the index columns must match the sort order exactly, or in reverse order, and must follow any equality conditions in the where clause. For an index on category identifier price, a query filtering by category identifier equals 5 and ordering by price can use the index for both filtering and sorting. If the query orders by price descending, the index can still be used, but the database scans the index backward. If the order by clause uses a column not covered by the index, or if the sort direction changes mid-index, for example, A ascending, B descending, a full file sort operation is required, negating the performance gain. A covering index is a composite index that includes all columns required by the query, both in the where clause and the select list. When the index covers the query, the database engine avoids the costly step of performing a table lookup, often referred to as a bookmark lookup or row identifier fetch. For a query selecting username, email, where the filter is on user identifier, the index should be defined as user identifier, username, email. Even though username and email are not used for filtering, their inclusion makes the index covering. This significantly reduces input-output operations, especially on systems where the index fits entirely in memory, but the main table does not. This technique is critical for high-throughput read operations.
Every composite index imposes a write penalty. Insert, update, and delete operations must update the B-tree structure, increasing transaction latency. Therefore, Only create indexes that address specific performance-critical queries. Furthermore, a composite index often makes single-column indexes redundant due to the leftmost prefix rule. If you have an index on A, B, C, the separate index on A is entirely redundant and should be dropped. The database optimizer will prefer the smaller single-column index if the query only uses A, but maintaining both wastes storage and increases write overhead. System analysts must audit existing single indexes after deploying a composite index to eliminate this redundancy and reduce overall database footprint. Database optimizers sometimes attempt an index merge, combining results from two or more single-column indexes using intersection or union algorithms. While this sounds efficient, index merge operations are computationally expensive, especially when dealing with large intermediate result sets. The database must fetch and sort row identifiers from multiple index structures. A well-designed composite index, however, allows the engine to traverse a single, highly optimized B-tree structure, drastically reducing the overhead associated with merging row pointers. If your execution plan frequently shows an index merge operation involving two columns, it is a strong signal to replace those single indexes with a single composite index covering those two columns in the optimal order. Before deployment, review the execution plan using Explain Analyze. Verify that the index is being used and that the rows examined count is minimal. Check for using file sort or using temporary indicators, which signal index deficiencies, particularly in the order by or group by clauses. Ensure the index column order prioritizes equality filters, then high-cardinality columns, and finally range filters. Audit the system for redundant single indexes that are now prefixes of the new composite index. Remember, composite indexes are powerful tools for specific query optimization, but excessive indexing degrades write performance across the entire system. Deploy strategically, measure performance impact immediately, and iterate based on real-world load.